Hello and welcome back to our review of our PG unit, Unit 4, Quadratics and Transformation of Parent Graphs. In this segment, I want to just go over our parent graphs and how we graph them and how our horizontal, vertical, and our dilation changes the graphs. This one you're familiar with, our quadratic. We have absolute value, we have radical function, we have our hyperbola, we have our cubic function, and our exponential function, which we will always have a base of 2. Now each of the parent graphs have a general graphing form that involves an A, an H, and a K value. And A, H, and K work the same in all of the general graphing forms. A is the dilation, which tells you the orientation, whether the graph is pointing up or down. If there's a vertical stretch, which makes the graph skinny, or a vertical compression, which makes the graph fat. And then we have a horizontal shift, where if H is positive, we move to the right. If H is negative, we move to the left. That is, it's always opposite of what it is. And we'll look at that as we look at the examples. And then K is the friendliest one because it is what it is. So let's take a look at some of the graphs and get the review going. For our absolute value graph, this is probably one of the easier ones to graph. We have our H value at 3 and our K value at -4, and our A value is at 1. So the absolute value graph is essentially two rays that meet at the vertex point. One ray going off in the positive direction and one ray going off in the negative direction. If we were to extend this line, we'd have a slope of -1. But the rise of the absolute value graph is always going to be A. We're always running 1, but the rise will always be A. And in this case, A is 1. And you can see how the domain and range is written. The domain for absolute values will always be all reals, and the range depends on where that vertex point is. And in our next example, we have a dilation of 2. Again, H is -2, and K is -2. So our vertex point is over here in quadrant 3. And now we have a vertical stretch. So instead of climbing up by 1, we climb by 2. So we'll run 1, climb 2, run 1, climb 2. And then you can see how the domain and range is written. Now if A turned out to be negative, then we just have an upside down V, and everything still works the same. Let's take a look at our next graph. The radical function is an interesting function. It's actually a parabola that's been turned on its side, but it's only 1/2 of the parabola. And it has a horizontal growth like a parabola, meaning that it grows, if we rise 1, we run 1, rise 1, run 3, rise 1, run 5. So the horizontal growth stays the same. It's the vertical growth that changes depending on the value of A. So for our first example, we have an H value of -1 and a K value of -3. So our vertex point is moved over 1 to the left and down 3. And then from there, we have an A value of 1, so we rise 1, run 1, rise 1, run 3, rise 1, run 5 to get this nice little curve. And you can see how the domain and range are written. The domain is the starting point of the x values, which H helps us with, and the range is the starting point of the y values, which K starts us with. Now in our second example, we have a dilation. Now the dilation only affects how fast the graph rises. It doesn't affect the horizontal growth. So here, our new vertex point is at -3, -2. And then from there, we rise 2 based on the dilation. We run 1, rise 2, run 3, rise 2, run 5. And if we continue this graph, rise 2, run 7, and so on. And then our domain and range, as you can see, written here. Let's take a look at our next graph. Our cubic function, we don't have a vertex point. We have what's called a point of inflection. It's a point where the graph goes from concave down to concave up. And that's the point that we want to keep track of when we do a horizontal and vertical shift. Now, for this particular graph, we have an inflection point at 2, -3. And when we graphed these in class, we realized, or we saw, that when a value is 1, that the next 2 points would be over 1, up 1, and down 1, over 1. And that just helps with the curve as we draw a graph. And the nice thing about the domain and range of cubics is it's just like a line. It's all reals. Now, when we have a dilation in a cubic, what that affects, it stretches the whole graph. It makes it more like a line. But when we graph this by hand, the point to the right and the point to the left of the point of inflection gets stretched by the dilation. So we'll run 1 and go up 3, and that's where the next point is. We'll run 1 and go down 3, that's the next point. And then after that, we can just do a nice curve. If we wanted to be more accurate with our graphs, we can do a table of values, but you can see how fast this graph grows if we plug in a value of -2. So if we have -2 here, we'll get 8 in here, because -2 plus 4 is 2, 2 cubed is 8, 8 times 3 is 24, minus 2 is 22. It's going to be way over here somewhere. So if we can just get those 3 points, the point of inflection, the one to the right and one to the left, we'll be okay. Let's take a look at our next graph. Our exponential graph poses a lot of challenges because we have to keep track of our locator point, which is at 0, 1, it's the y-intercept, and our asymptote, which is the k-value. Now, in this particular graph, we have a horizontal asymptote at -3, and that's the first thing that goes on the graph. You sketch the horizontal asymptote, and then what I've recommended that students do is draw kind of like the phantom graph, what the parent graph would look like, the y equals 2 to the x, and then all we're doing is shifting all those points down 3. So our locator point goes from 0, 1 to 0, -2. And then all the points follow. So, and then we can just draw a nice curve going up. And the domain for exponentials will always be all reals, and the range is dictated by our k-value. And notice it's not inclusive, because that's an asymptote. The graph gets really close, but never touches -3. Now our next example, we have both a horizontal and vertical shift for our locator point. So we're going to start with drawing out the horizontal asymptote, which is right here, y equals -4. And then we're going to put our phantom graph, y equals 2 to the x, here. And then all we're going to do is we're going to move our graph 3 to the left and 4 down, and find our new locator point at -3, -3. All these points follow the shift. So if you can just grab them all, move them 3 over to the left and 4 down, we get our new graph. Okay. Now if 2 ended up being negative, then this whole graph would reflect over the asymptote. So for example, let me get color here. a different color. So let's say we had y equals negative 2x plus 3 minus 4. So it would be the same graph, but everything would flip over. So we would be over here at negative 3, negative 5. And the graph would look something like that. So you just take all these points, and reflect them over our asymptote. Okay, let's take a look at our next parent graph. Our hyperbola, our inverse graph. It's its own inverse. We'll talk about inverses in a couple of units. But notice that you have two branches, and we talked about how these branches grew. As we go farther out on the x, meaning we put a bigger value here, the value y gets smaller because 1 divided by a big number is a small number. And we saw as we move closer to 0, meaning when we're putting a smaller number here, and we divide 1 by a small number, we get really big in a hurry. And the same goes for if we take out a negative number along this way. As we get a bigger negative, a smaller negative number, like negative 10, so forth, we get closer and closer to 0. And as we get closer and closer to 0 this way, we get bigger on the negative going this way. So the domain and range will always be where the asymptotes are. So we have an asymptote at x equals 0 and y equals 0. So we write x does not equal 0 and y does not equal 0. It could be any other point except for those two. And then we have a locator point, which is the center of the circle. So let's take I'll look at a couple of examples here. So HK tells us where asymptotes are and helps with domain and the range. So H here is negative 3, K is negative 2. So we put in the asymptotes, x equals negative 3 and y equals negative 2. Our new locator points at negative 3 and negative 2, and we just draw our nice curve hugging both the vertical and horizontal asymptotes on both branches. And then our domain and range are related to h and k. Since h is at negative 3, our domain could be anything except for that value, because it makes 1 divided by 0, which is undefined. And then as this value gets closer and closer to 0, our y values get closer and closer to negative 2. So it'll never touch at negative 2. Okay. Let's look at one more example. Here we have a h value at 1 and a k value at 2. So that helps us with the asymptotes. And it helps us with the domain. So x can be any value except for 1, and y can be any value except for 2. And then I forgot to write our new center point here. So the new center point ends up being 1, 2. Okay. I hope you found this helpful. Take your time, look at the examples over and over if you need to. And if you need a little bit more help, then come visit me in the morning or after school. Until next time, bye-bye.